The first issue concerns wire size and breaker rating. A code violation exists. National Electrical Code Section 240.4d states the ampacity of the ungrounded conductors must not exceed the ampacity of the overcurrent protective device. The 500 mCMTHHN wire has an ampacity of 490 amps according to Table 310.16, which is less than the 600 amp rating of the breaker. National Electrical Code Section 240.21b4 applies to taps not exceeding 25 feet in length. Since the conductors are 60 feet long, this exception does not apply. The second issue involves grounding. This also constitutes a code violation. According to National Electrical Code Section 250.148c, grounding conductors shall be connected to a grounding terminal or grounding electrode conductor at the service entrance or at each disconnect or junction box in a wiring system. A grounding lug should have been installed in the disconnect to connect the grounding conductor of the incoming power supply. National Electrical Code Section 250.112e requires the grounding conductor of a branch circuit to be connected to the equipment grounding terminal of the load side device. Connecting the grounding conductor for the load side to the grounding bushing would not have met this requirement. To reiterate, both situations described are code violations. It's important to ensure electrical installations comply with the National Electrical Code to ensure safety and proper operation. The wire size should be increased to match the breaker rating, and a grounding lug should be installed in the disconnect to connect the grounding conductor. Let's delve deeper into the specific code sections and considerations involved in this scenario. Firstly, let's discuss conductor ampacity and overcurrent protection. The National Electrical Code, specifically Section 240.4d, establishes a fundamental principle for electrical safety: the ampacity of the conductors must be protected by the overcurrent device. This means the breaker or fuses must be sized appropriately for the wire they are protecting. The primary goal is to prevent conductors from overheating and potentially causing a fire due to excessive current flow. In this case, the installation used 500 mCMTHHN conductors, which have a listed ampacity of 490 amps according to National Electrical Code Table 310.16, assuming a 75°C termination temperature. However, these conductors were connected to a 600 amp breaker. This immediately violates the code because the breaker is rated to allow more current than the conductors are safely capable of carrying. If a fault or overload condition occurs that draws between 490 and 600 amps, the conductors could overheat before the breaker trips, leading to insulation damage and potentially a fire hazard. It is important to select conductors with an ampacity equal to or greater than the rating of the overcurrent device protecting them. Several factors influence a conductor's ampacity, including its size, insulation type, installation method, and ambient temperature. National Electrical Code Table 310.16 provides ampacity ratings for various conductor types and sizes under specific conditions. However, it's crucial to apply the appropriate correction and adjustment factors based on the actual installation conditions as outlined in National Electrical Code Sections 310.15b through 310.15b3. For example, if the conductors are installed in an area with a high ambient temperature or are bundled together with other current-carrying conductors, their ampacity must be derated to account for the increased heat. In this particular scenario, the electrician considered using the tap rule under National Electrical Code Section 240.21b4 to potentially justify the smaller conductor size. The tap rule allows for smaller conductors to be used to tap off a larger feeder under specific conditions. However, this exception only applies if the tap conductors meet certain requirements, including limitations on their length and the overcurrent protection provided. Specifically, National Electrical Code Section 240.21b4 applies to taps not exceeding 25 feet in length. Since the conductors in this case were 60 feet long, this exception does not apply. The tap rule is intended for situations where the smaller conductors are run a short distance to a specific load and are protected by a separate overcurrent device at the tap point. It is not intended to allow for undersized conductors to be used for the entire length of a feeder run. Therefore, the electrician's attempt to apply the tap rule in this situation was not valid, and the installation remained in violation of the code. To correct this violation, the electrician would need to replace the 500 mcm THHN conductors with a larger size that has an ampacity equal to or greater than the 600 amp breaker rating. Alternatively, the electrician could reduce the size of the breaker to match the ampacity of the 500 mcm THHN conductors. However, this may not be feasible if the compressor requires a 600 amp breaker for proper operation. Now let's discuss the second code violation concerning grounding. Proper grounding is essential for electrical safety. It provides a low impedance path for fault current to flow back to the source, allowing the overcurrent device to trip and to energize the circuit in the event of a ground fault. The National Electrical Code outlines specific requirements for grounding systems to ensure their effectiveness. In this case, the electrician initially considered landing the grounding conductor on a grounding box connector or bushing, which would have eliminated the need for a grounding lug in the disconnect. This approach would have also connected the grounding conductor for the load side to the grounding bushing. However, this is a violation of National Electrical Code Section 250.148c, which requires grounding conductors to be connected to a grounding terminal or grounding electrode conductor at the service entrance or at each disconnect or junction box in a wiring system. This means that a grounding lug should have been installed in the disconnect to provide a dedicated termination point for the grounding conductor of the incoming power supply. The grounding lug ensures a secure and reliable connection between the grounding conductor and the metal enclosure of the disconnect, providing a lower impedance path for fault current. Furthermore, National Electrical Code Section 250.112e requires the grounding conductor of a branch circuit to be connected to the equipment grounding terminal of the load side device. If the grounding conductor for the load side had been connected to the grounding bushing, this requirement would not have been met. Connecting the load side grounding conductor to the grounding bushing would not provide a direct connection to the equipment grounding terminal of the compressor, which is necessary to ensure proper grounding of the equipment. To correct this violation, the electrician properly installed a grounding lug in the disconnect and connected the grounding conductor of the incoming power supply to the lug. This provided a dedicated and reliable grounding path for the disconnect and ensured compliance with the National Electrical Code. In addition to the specific code violations discussed, there are several other considerations related to the electrical installation for a 300 horsepower air compressor. Firstly, it is crucial to properly size the conductors based on the motor's full load current rating and any applicable directing factors. National Electrical Code Section 430 provides detailed requirements for motor circuits, including conductor sizing, overcurrent protection, and disconnecting means. Secondly, it is essential to select the appropriate type and size of overcurrent protection for the motor circuit. Motors have unique starting characteristics that require special consideration when selecting overcurrent protection. National Electrical Code Section 430 provides guidance on selecting the appropriate type and size of fuses or circuit breakers for motor circuits. Thirdly, it is important to install a disconnecting means within sight of the motor and controller. The disconnecting means allows for the motor to be safely de-energized for maintenance or repair purposes. National Electrical Code Section 430 provides requirements for the location and type of disconnecting means for motor circuits. Finally, it is crucial to properly ground all metal enclosures and equipment associated with the motor circuit. Grounding provides a low impedance path for fault current and helps to prevent electrical shock hazards. National Electrical Code Article 250 provides detailed requirements for grounding electrical systems and equipment. In conclusion, the electrical installation described contained two code violations related to wire size and grounding. To ensure safety and compliance with the National Electrical Code, it is essential to correct these violations and follow all applicable code requirements for motor circuits. Always consult with a qualified electrician or electrical engineer to ensure that electrical installations are performed safely and correctly. Here are some additional points to consider regarding the initial situation and the code violations that occurred. Firstly, the pressure to complete the work quickly, particularly on double time, should never compromise safety or code compliance. Electrical work requires careful planning, attention to detail, and adherence to established standards. Rushing the job can lead to mistakes and potentially dangerous situations. Secondly, disagreements among electricians on a job site are not uncommon. However, it is crucial to have a clear process for resolving these disagreements and ensuring that the final installation meets code requirements. In this case, it may have been beneficial to consult with a supervisor or a qualified electrical inspector to clarify the code requirements and ensure that the installation was performed correctly. Thirdly, the fact that the wire had already been shipped in for the job should not have been a determining factor in the decision-making process. While it may have been inconvenient to return the wire, it is always better to correct a mistake than to proceed with an unsafe or non-compliant installation. Fourthly, the potential for future modifications or upgrades should always be considered when designing and installing electrical systems. In this case, the electrician should have considered the possibility that the fuses in a disconnect could be upsized in the future and sized the conductors accordingly. Fifthly, proper communication and documentation are essential for electrical work. The electrician should have clearly documented the wire size, breaker rating, and grounding methods used in the installation. This would have helped to prevent misunderstandings and ensure that the installation could be easily inspected and maintained in the future. Sixthly, continuing education and training are crucial for electricians to stay up to date on the latest code requirements and best practices. The National Electrical Code is updated every 3 years, and it is important for electricians to be familiar with the latest changes. Seventhly, electrical inspections play a vital role in ensuring the safety and compliance of electrical installations. A qualified electrical inspector can identify potential code violations and ensure that the installation meets all applicable requirements. Eighthly, it is important to remember that the National Electrical Code is a minimum standard for electrical safety. In some cases, it may be necessary to exceed the code requirements to ensure the safety and reliability of an electrical installation. Ninthly, electrical work is inherently dangerous, and it is important to take all necessary precautions to prevent electrical shock and other hazards. This includes wearing appropriate personal protective equipment, using insulated tools, and energizing circuits before working on them. Tenthly, it is always better to err on the side of caution when it comes to electrical safety. If there is any doubt about the proper way to perform an electrical task, it is best to consult with a qualified electrician or electrical engineer. Remember, electrical safety is everyone's responsibility. By following code requirements, using best practices, and taking all necessary precautions, we can help to prevent electrical accidents and ensure the safety of ourselves and others. Always prioritize safety and compliance over speed or convenience. Electrical work is not something to be taken lightly, and it is important to approach each job with professionalism and attention to detail. It is also important to remember that the National Electrical Code is not just a set of rules to be followed, but a comprehensive guide to electrical safety. By understanding the principles behind the code requirements, electricians can make informed decisions and ensure that electrical installations are performed safely and correctly. In addition to the technical aspects of electrical work, it is also important to have good communication and interpersonal skills. Electricians often work in teams, and it is essential to be able to communicate effectively with coworkers, supervisors, and customers. Good communication can help to prevent misunderstandings, resolve conflicts, and ensure that everyone is on the same page. Finally, it is important to take pride in your work as an electrician. Electrical work is a skilled trade that requires a high level of knowledge, skill, and attention to detail. By taking pride in your work, you can ensure that you are providing your customers with the best possible service and contributing to the safety and reliability of electrical systems. So to sum everything up, wire size needs to match the breaker, grounding needs to be done correctly, and safety should be a priority.